In this lesson, we're going to talk about one of the most difficult topics typically for students, which is called optimization. There's a lot of application here, so you'll have to take your calculus skills and apply them to problems with physical or economic or, even abstract as well. Applications. So it might be a farmer is making a fence that he only has a certain amount of fencing and he's trying to give his cattle the largest space they can possibly graze in. That sort of problem where you're going to have to organically come up with some sort of equation that binds all these things together and then work with it in the context of calculus to find the optimal situation. Usually it means finding a minimum or a maximum. In the case I just described to you, it would be maximizing area with a constraint of perimeter. Because he only had a certain amount of fence, and he wanted to get as much clover or whatever on the ground available to his cattle that he could possibly get, or her cattle, sorry. There's a PDF, again, associated with this video, so you might want to pull that up. What I'd like you to do first, actually, is just hit pause, go to that PDF, and the first question there about a brownie pan, just take 15-20 minutes, and I actually mean that. Don't take 5 minutes and call it 15 or 20. Take 15 or 20 minutes and really think about how you can get the largest possible, volume of brownies in that pan. And the basic idea is you have an 8x8 sheet of metal. You're going to be cutting out congruent squares from the corners and then folding it up. So you got your sheet of metal, that's supposed to be a square, and then you're going to cut out squares here, and when you fold the sides over, when you remove the corners after you've cut them out, when you fold those sides up, now you'll have a little brownie pan that has a certain height to it. So you're going to try to optimize that volume. You might want to use guess and check. You might want to think about how you can use calculus. But just go ahead and do that now, and then come back and resume the video when you get a chance. Okay, so now we're actually going to solve that. I should not have erased my beautiful drawing. Okay, so these squares, once these squares go away, what we're basically looking at is the rest of these sides folding up. And of course the squares have to go away so that you get nice corners. And this whole side was 8, but of course the side of the pan, and I'm fully aware that this is nowhere near square, the side of this pan will no longer be 8 inches. Because we'll have folded some of it up. So what I'm going to do is call my cuts, I'm going to call them x by x. Right? These are all x by x. Which means that this measurement, the measurement of the pan now, is 8 minus 2x. This measurement right here. And of course all of those are. And when we bend the pan up, the new height will be measured x. Okay. So now we're going to write an equation for volume. The volume of this thing will be 8 minus 2x squared. That would be length times width times height. Now you're not prompted with this volume equation ahead of time or something like that. These will not be contrived at all. You'll have a situation where you have to be dynamic about your decision of which formulas to be using, and also sometimes it's not even something that has like a very cut and dry formula. So anyway, now we could expand this thing out and you'll get 64x minus 32x squared plus 4x cubed. So check my math there, hopefully everything is good. Yeah, it looks pretty good to me. I've distributed the x in as well. Now what we're going to do is take v prime. v prime will be 64 minus 64x plus 12x squared. What we'll do with this, if we want to try to find where the volume is maximum, think about the volume as some curve. You know, the volume where this is your x value and this is the volume. If the volume is some curve, to find its maximum volume, you know, something like that maybe, we'd want to know where these points are at the top of our curve, which we're familiar with finding minimums and maximum values. So what we're going to do is set that guy equal to 0. And I'm seeing I can divide everything by 4. So 16 minus 16x plus 3x squared and then you can factor. So 3x minus 4 and x minus 4. So when you solve this, you get 4/3 and 4. The first thing I think about, though, when I do these is I should be always, not the first, but as I'm working on this process, I'm always concerned about my domain. Because some of these values may produce minimum values and maximum values, but may not be practical in the context of the question. So in this case, x equals 4, that thing has got to go. Because if we were to cut a square out that's 4 by 4, our pan's only 8 inches tall or wide, we would actually cut the thing so that it has no volume at all, right? If you cut out a 4 by 4 square here, there'd be no bottom to the pan. So that one's out. So really, our major candidate is going to be either 4/3 or our endpoints. In this case, our endpoints of our domain would be to make no cut at all, aka 0, or to make a cut of 4 inches, because that's the largest cut we can make, and we of course already have realized that that makes no a 0 volume. So 4/3 must be the optimal cut. So if these are 4/3, then the dimensions of the pan, 8 minus 2 times 4/3, it'd be 8 minus 8/3, which is 5 and, wait, 8 minus 8/3, 5 1/3 by 1 1/3, I guess. Whatever the case is, x equals 4/3 produces our maximum. If you wanted to actually know what that volume was, you take 4/3 and you substitute it into the original volume equation, and you'll know the maximum amount of awesome brownie mix you can pour into it to get real thick, fat brownies. Okay, so on the next page of the PDF now, if you look at that, I've given a sort of step-by-step process by which you can optimize things. The first thing is determine what you're going to optimize, in this case volume. The second is determine a primary equation, right? So we need to write a primary equation, in other words, an equation having to do with volume in the context of this question. That's often a very hard step. Sometimes we also write a constraint equation. In this case, I chose not to. The constraint would have had to do with the fact that this is 8, and any cut here determines the size of that. You'll see more constraint equations soon. The domain of this equation, as I said, in the context of this problem, you can make a cut of 0 or as large as 4, and then take the derivative and solve the problem. Okay, so I'm actually going to skip to the rectangular page containing 24 square inches of print. Question. If we have a rectangular page, it is to contain 24 square inches of print, but we're also guaranteed, we're also guaranteed that it has to have a bottom margin of 1.5 and a top margin of 1.5. So from there to there, that's 1.5. That's 1.5. And then the left and right of the page have to be 1 inch. And this is where my writing goes. And we want the area of that to be 24 square inches. We're trying to use as little paper as possible. So we basically want to know what size of a page do we need given those margins. So what you need to do in this case, and I'm not going to go through every single step here, but what we need to do is figure out, is it, for example, is it 12 by 2? Do we want a book that's very thin and long, or a taller book, or do we want a perfectly square book? And all of that will be determined basically by the following. If we you can either let the page, this width be X. Let's let that be X, and that be Y. Now, the entire page's area will be X plus 3. Right, I say plus 3 because there's 1.5 inches here and here, plus the height of the page. And then Y plus 2. And at this point you think, uh-oh, I have two variables, I can't take the derivative of it. That's where a constraint equation comes in. So the constraint here is that the area of the type has to be 24 square inches of print. Sorry, students outside. If it's 24 square inches of print, then what we can do is write an equation that says xy must equal 24. So therefore, y is equal to 24 divided by x. Now this is useful because we can rewrite our area as x plus 3 times 24 over x plus 2. Now you can distribute that out, take the derivative, find minimum values minimum values so that you can minimize the amount of area of the page used. So again, the general process is write an equation of the thing that you care about. Then try to simplify that equation. Oftentimes you're going to have to involve a second equation by which you can isolate one of the variables, or in which you can isolate one of the variables. And then take that thing and use calculus. Derivatives, set them equal to 0, find minimum or maximum values as needed. This will take a lot of practice to get good at optimization. So feel free to do any of the problems on the PDF. And also, of course, homework questions. I put a problem set out there. The book has tons of examples, so please use all these things. It will be difficult, but with more practice, it gets easier and easier. Thanks.